Now we will switch a little bit. And, you know, at least for my side, AI and cybersecurity is my business. This is where I'm getting my salary. But the one which I think will be the most important one, and I'm really, really looking forward to see a big change, is AI and medical. Imagine yourself that you can take a medical image, upload it to some cloud service, and using AI, I don't depend on any doctor. He's tired, he has some problems, he can miss some important thing about my medical situation. So AI can really change the way we are getting an improvement in the medical sector. So our next speaker will connect AI and medical. So I would like to invite Professor Hayit Greenspan, where she is a professor at the Tel Aviv University. She got her PhD from Caltech, from California Institute of Technology. She already published more than 150 papers. She is a co-editor in the most attractive and leading publishers around the world, including the IEEE. So if you like to publish a paper, contact her probably later, it will help. So, Professor.
Okay, thank you very much. Okay, well, yeah, I do feel like I'm a little bit taking you to a different domain. I'm not going to show you many issues to worry about, more like hopes for the future of where we're going using deep learning technology. I head the Medical Image Processing Lab at the engineering faculty at Tel Aviv University, and I'd like to share a little bit of what we do there. So imaging, I'm focusing on imaging, and imaging is medical imaging. It's growing in numbers. Actually now it's part of everything you do medically in a medical treatment, from the diagnosis stage to determining treatment and then follow-up of the treatment. And we see that the imaging acquisition has improved substantially. There's a lot of work in getting the machines to be more higher resolution, more accurate. So now we see thousands of images coming from each one of these modalities. So we have thousands of images, overall something like 5 billion studies per year worldwide. But we forgot one thing, and that is the radiologist. The radiologist is in fact doing the same procedure that he's been doing for many, many tens of years. And he receives all this information. Previously it was 10 slices, now it's 100 slices. Sorry, now it's 1,000 slices, right, per case. All this information is stored in a PACS, which is the basically the storage of all this imagery. And then slowly but slowly, he reads out the cases from the PACS, and he needs to review them. So there's limited time to review an increasing number of images. And this leads to many issues like missed findings, long turnaround time, and of course there's no time to really measure things, quantify things, which is critical for especially follow-up diagnosis. So it's definitely time to put in computational tools to start and support the diagnostician, the radiologist, the oncologist, and so on. And the computational tools that I work on and my colleagues have to do in the image analysis domain, and specifically what we can call AI. And for us, it's become deep learning in the last few years. Just notice in the diagram here that all these different modalities go in some kind of a processing, or that's what we're proposing to do, and then they will go into the PACS, which was the storage, and also can affect the reporting system. So in fact, just to close this loop here, the radiologist reads in the image from the PACS, the output of the radiologist goes to the reporting system. So input is an image, and output is in fact text, a report of a list of findings, right? So with deep learning, we can, or with any kind of machine learning, we can try and analyze the images, possibly even before the radiologist sits down to look at a case, and get what we can call metadata out from these images. And the metadata can be any kind of information about the images, inside the images, labeling of the images, if there are any kind of findings that we can detect, and measurements and characterizations of these findings. So in order to do this, we want to bring in AI or machine learning into the medical imaging domain. And we had a very big question if that was even possible a few years back, specifically deep learning. And that is because deep learning requires a lot of data, as was already mentioned here. Maybe not stressed too much, but I'm going to stress it here because in the medical domain, we have a problem with data. There isn't enough data. Okay, so we can see that in like general vision tasks, we can get millions of images, and that gave us a breakthrough, in fact, with this ImageNet data set that was collected. And we have, in many challenges around, we have hundreds of thousands of images and so on. But we want to look at specific medical tasks. Okay, so let's say we want to address something to do with the liver, and we want to find a pathology, a finding in the liver. Then when we go out and we use our, share our colleagues and ask to get the images, we work very hard to get this data. And this data is coming from hospitals, from clinics, and so on. So we're very happy and pleased when we get this amount of images for a certain task. We're talking about hundreds of cases, sometimes even less, for a certain pathology or finding that we want to address. Okay, so the challenge is that it's limited data. And of course, we have a problem of expensive data annotation. So of course, data is data, but it becomes more meaningful, we can learn from it, if we can train. And training means that it has to be in some way supervised and annotated for us, right? So if we want to have that kind of supervision and annotation, we have to go to, again, to the medical expertise and ask the expert to sit down and label things for us. It's a very, very long, expensive task. So our challenge, in fact, is to be able to cope with this data challenge. And we are able to do so, and I'd like to show you some highlights today. We have many, many cases that have successes, and I'll show you a few of them. Already in 2016, we came out with a special issue on deep learning in medical imaging with several groups contributing, and 2017 was the first book out that I co-edited on deep learning for medical image analysis. And since then, many, many books, explosion of information and books and publications in this domain. So I'll show you a few highlights. I should mention that in my lab, we have work from the cellular level, microscopic images, to what you see here, X-ray, CT, MRI, and so on. So from the cellular level to the brain, and in each one, it involves collaboration with the radiologists, with the medical expertise. So let's start with X-ray. I'll show you a few examples. Let's start with X-ray. And X-ray is a very simple kind of image, right? We have a single image coming out. And here you see images of chest. This is a healthy chest. And here you see an enlarged heart, some liquid in the lungs, which is called pleural effusion, and another pathology, large mediastinum here. Okay, so it turns out that when you take this single image, you can already find out if the radiologist had the time to look at this image, he would say, yes, chest is okay, or no, there is some pathology in it. So why is this interesting for us? Well, it's interesting because that's the modality that has the most amount of data, like 2 billion procedures a year. The first thing you do is you get an X-ray. And the problem is there aren't enough radiologists to look at these X-rays anymore. And in every hospital around the world that I visited, there's always this concern. There's not enough radiologists to look at the X-rays that all of us are taking when we go into the hospital. And in fact, there are losses, human loss, just because it took too long for a medical expert to look at this X-ray while the patient was waiting in the emergency room. So this is, in fact, a critical domain, and possibly we can support it with computational tools. So this is something I started with my colleague, Professor Konen, from the head of radiology at Sheba Medical Center quite a few years ago. And we collected cases, and he, in fact, annotated them for me. And we slowly increased our data set, and we're now at something like 400 cases per pathology. It's definitely not big data. What can we do with this amount of data? So the first question we asked was, can we, in fact, use deep learning, right? So we were all excited about deep learning in computer vision. And in the 2013, 14, and so on, and published in 2015, we actually were able to show our first works showing that, yes, there is something that's going on in these networks that can help us in the medical domain. So the first thing we did was transfer learning. Okay, so what is transfer learning? It's basically learn something, one thing, and then see if that information can help you learn another thing in a different domain. The question was, can we use the ImageNet, which is this collection of images having to do with everything in the world that you see in natural images, from clocks and animals and planes and sunsets and whatever, okay? Use the network that was learned on these millions of images, and now it knows very well to classify between these categories, thousands of categories, and then introduce a new test image which is coming from the image from the medical domain, like an X-ray, right? So basically that's what we did. We introduced this X-ray. We read out from the network the representation that was learned when this input was entered, extracted out this representation from layers within this network, and then used that representation with a regular classifier to categorize if there is one pathology, like the enlarged heart, if there is another pathology, like fluid, and so on. So notice that in this case, the scenario is that we can have multiple labels. So this is actually a multiple label scenario, okay? One case may have several categorizations, and this is in fact such a case. And in 2015, we found out that this is in fact possible. So we see here our results that are 90% sensitivity and getting close to, well, 85%, let's say, or now it's even getting close to 90% specificity, which is in fact anything above 85 to 85 is considered clinically of interest. Okay? Recently, we're starting to see data coming out that's from challenges that has like hundreds of thousands of images. So these are taken, this is very noisy data without the expert actually sitting down and annotating them, but rather reports being read. And with this new data sets, we're getting a lot of new things that we can work with. And you see that on this data set with more findings here, we're still getting above state-of-the-art results. It's been improved since then, and some localization capabilities as well. Let me go quickly to another domain. So CT, I'll show you an example of the liver. We want to segment the liver automatically. We want to find lesions within the liver. We want to characterize these lesions. Are they malignant or benign? Possibly categorize them even further to different categories. And we can help in any one of these stages that you see here on the left. So in fact, we want to provide tools to help and support the radiologist in the day-to-day work, and specifically save the tasks that are tedious for the human and more possible for a computer, leaving the more interesting tasks and diagnosis decisions for the expert. So a few of our works in this domain, for example, we can introduce new networks to segment a full CT volume. By taking a few slices each time into these networks, we can find out, get the segmentation maps out. And these segmentation maps, again, are trained on very limited data, like 20 patient data, okay? But we are able to get them results out that are very nice, as you see here. We see automatic liver segmentation from the CT volume, automatic lesion detection within the liver, and results that are very promising at this point, reaching close to 90% true positives with very, very low false positives. Now, this is something critical for us. Not only do we want to be highly accurate, but we want to be very, very low false detect, so we don't alarm when there's no need to. We don't want to introduce more work to the radiologist. So in fact, we have to keep the false positives very, very low. Let's go a step forward. Let's say we found those lesions, and now we want to identify what type are they. Okay, so here's a case where we have, again, we collected from Sheba Medical Center some cases. We have 50s, 60s, and so on of these different types. Cyst is benign, metastases, malignant. Hemangiomas look very much like metastases, but are in fact benign. So knowing which one you're looking at is critical for your kind of treatment that you're providing. We took a network, takes one of these regions around a lesion, and then we have to identify, is it one of these three categories, right? But we only have 182 lesions. Definitely a data problem, right? So how do we solve this challenge? Well, one way to solve a data problem is to augment it. And augmentation is very well known, and the classical techniques to augment data is to rotate and flip and translate and whatever you want to do with your data set. What you can also do is start doing something more advanced, and that's something we've been playing with for the last couple of years, and that is using the GAN networks, generative adversarial networks, to synthesize and augment the data. So we have here a case of real data and synthetic data. Okay, and in fact, we were able to show that when we add the synthetic data, we're able to increase our performance, and we increase our performance by 7%, which is in fact very, very substantial. Even more, we can go to some more interesting things. Not only augment the lesions that we have, but maybe even introduce new modalities. Synthetically generate modalities. This is something that's really going on. It's exciting, going from MRI to CT, from what I'll show you here, is going from CT to PET. So PET is actually something that helps you diagnose if it's a malignancy or not. Okay? It helps the oncologist greatly and helps identify if the lesion you're looking at is malignant. But we don't have PET in most clinics, and it's expensive and it's radioactive. So how about if we introduce virtual PET? So we can go from CT to PET, and you see here real pairs, and this is our production of new PET. And this basically what we're showing here is that it decreased our false positives by close to 30%. So the PET, this virtual PET, is giving us capabilities that we didn't have before. So are we there yet? Will AI enter the clinics? Well, we're quite close. It's getting there. If you ask Hinton, people should stop training radiologists now. We didn't like the fact that he said that, and the community didn't like it, and he scared all the radiologists away. And it took us a couple of years for them to relax and say the following: it's not going to replace us, it will redefine us, which is where we're heading. And that is giving them the tools to do their work, but in a better and more advanced way. So these are some of the challenges ahead, specifically the data challenge. This is interesting for this community here. We have issues with PHI, HIPAA compliance, privacy issues. How are we going to get more data from the hospitals, specifically when we want to go to fuse data from many more sources surrounding the patient? So we want to get more and more data about the patient. That will require communication of many, many sources. Many opportunities ahead, and I'm definitely positive that we're going to new medicine and new treatment, more personalized treatments, but based on a lot of knowledge and a lot of learning. Thank you very much.
Professor Hayat, thank you very much. So we will move now to